Welcome to section 1.7 over linear independence. In this section, we'll kind of look back to the material we learned in section 1.5 over homogeneous equations. And now we're just going to take things a bit further and write them as vector equations. So recall that a homogeneous system of this form here always has that trivial solution of x equals 0. And we're ultimately concerned about if there are any other solutions or non-trivial solutions. And a lot of times we will write this as a linear combination, and they are given different weights. And if we put these together, we'll get to what we're talking about today, which is linear independence. So here is the definition. A set of vectors is considered to be linear independent if this vector equation, so we're just rewriting it as a vector equation, if it has only the trivial solution. So only that solution of x equals 0. If that is not the case, then it is linearly dependent. And this is what we're going to analyze today. So here, it's just restating that definition. The columns of this matrix A, so this is just a specific example, are linearly independent if and only if the equation ax equals 0 has only the trivial solution. So let's see what this means. So let's say I have this matrix here, and we want to know if these columns are linearly independent. Okay, well, we need to see what's happening. So I can row reduce this matrix to this one here. And if we look at this, this tells us that we do have a free variable because we have that row of zeros here. Okay, if there is a free variable, if that free variable exists, then that tells us that there is a non-trivial solution other than that trivial solution of x equals 0. And if there is a non-trivial solution, then we can conclude that the columns are linearly dependent. Let's look at another type of example. Okay, so now this one's set up a little bit different. I've given you 3 different vectors here. And we want to determine if the set of vectors is linearly independent. Okay, so if there is a non-trivial solution, so if a free variable exists, then it's linearly dependent. So what we're going to do is we're going to set up a matrix, row reduce it, see if there's a free variable. If there is a free variable, then no, it is not linearly independent. Okay, so let's take a look at this. So in part A, the set will be linearly dependent. So I'm just going to write this down. The set will be linearly dependent. I'm going to shorthand. If the following occurs. So if x1 times this vector, so remember this is vector 1, plus x2 times vector 2 plus x3 times vector 3. If this is equal to 0, if this has a non-trivial solution, so in other words, if x1, x2, or x3 does not equal 0, or if a free variable exists, then it will be linearly dependent. Okay, so this is something we've done before, nothing new. It's all the same, it's just written in different ways. Okay, so here's our matrix. We want to row reduce this. You are certainly able to do this by hand if you need the practice. So if you put this in reduced row echelon form, you get the following matrix. So here, this last row of zeros tells us that we're going to have a free variable. Remember, this represents x1, x2, x3. So we have a pivot, pivot, no pivot in this column here. So that means x3 is a free variable. Since there is a free variable, this implies that our equation has a non-trivial solution. And that this set is linearly dependent. Okay, so because it is linearly dependent, we can go ahead and answer part B, which is finding a linear dependence relation. Now with this, there are an infinitely many number of possibilities, because since x3 is free, depending on what I choose for x3, I'll get a different relation. So let's do this on the other slide. Okay, so I'm just going to quickly rewrite this matrix. And show you that this can be written in the following way. So I have x1 minus 2x3 is equal to 0. X2 plus x3 equals 0. And then 0 equals 0, indicating that x3 is free. So like the other problems we've seen in the past, we like to isolate these variables. So x1 is equal to 2x3 and x2 is equal to negative x3. So here, once again, what we want to do is we want to pick some value for x3. There were no restrictions given to us, nothing was stated that we need to consider. So let x3 be anything you want. I'm going to say let x3 equal 2. If x3 is 2, then I can plug 2 in to these and find that x1 is 4 and x2 is negative 2. Okay, well, I set up that equation earlier, and I can rewrite that equation using vectors. So x1 times vector 1 plus x2 times vector 2 plus x3 times vector 3 equals 0. And what I'll do is I'll just plug in, and instead of these vectors, remember I had matrices. Okay, so for x1, x2, and x3, I'm just going to plug these in. So I have 4 times vector 1 plus, or I guess minus 2 times vector 2 plus 2 times vector 3 is equal to 0. So this is one of infinitely many possible dependence, linearly dependence relations among those three vectors. Okay, here is another type of problem. It's the same thing, just written a little differently. So now we want to determine if these columns of the matrix form a linear independent set, and we want to justify. Okay, so I want to remind you that the columns will be linearly independent if and only if this equation, x1 vector 1 plus x2 times vector 2 plus x3 times vector 3, because there are three columns, if this is equal to the 0 vector, this implies that x1 or x2 or x3 equals 0. Okay, so we just want to see what happens. Okay, great. So once again, I'm going to set up my augmented matrix. Because this is an equation, we'll want to put in that 0 column. And then we will row reduce this. You can do it by hand, you can plug it into your calculator, whatever works for you, but this ends up being equivalent to the following. Okay, so here we can make some observations. We have some pivots, but no pivot here. We have this row of zeros. This tells me that I have a free variable. This is telling me that x3 is free. So if I have a free variable, this tells me that there is a non-trivial solution. If there is a non-trivial solution, this tells me that the columns are linearly dependent. And that concludes this example. So now we're going to talk about some definitions and theorems. Basically, if we have a set consisting of a single non-zero vector, so for example, if I have something like this, then I can rewrite the equation like this. So this will give me only the trivial solution, implying that it will be linearly independent. This one here comes up a lot. The set of two vectors is linearly dependent if one is a multiple of another. Then we have this theorem here. Theorem 7 says that the set of vectors is linearly dependent if and only if at least one vector in the set can be written as a linear combination like that of other vectors. Now there are some things to specify here. Theorem 7, that previous theorem, does not say that every vector in a linearly dependent set is a linear combination of the preceding vectors. It says at least one vector. And a vector in a linearly dependent set may fail to be a linear combination of other vectors. Okay, so just a couple things to mention. Another theorem, Theorem 8, comes up quite a bit in your homework. It says that if a set contains more vectors than there are entries in each vector, then the set is linearly dependent. So basically, if you have 4 vectors, and they each have 2 entries, this would be linearly dependent. Let's look at an example. It says analyze the following vectors here. Here, these vectors are considered to be linearly dependent by Theorem 8 because there are 3 vectors in the set and there are only 2 entries in each vector. Now, another thing we talked about is that a set of vectors is linearly dependent if one is a multiple of another. Now, if we look at this, each of these 3 vectors are graphed here. These are not multiples of one another. Since they're not multiples of one another, we can say that they are, once again, linearly dependent, not independent. Theorem 9 says that if there's a set that contains a 0 vector, then that set is linearly dependent. So if I have this set here, because we have this 0 vector, it is said that this is linearly dependent. So let's put this together, and just by looking at these vectors, let's determine if these are linearly independent or not. So basically, we're going to use the definitions and theorems that we have just been exposed to. Now, the easiest one is Theorem 8, in my opinion, and that one says if there are more vectors than entries, then it's linearly dependent. So in the case of part A, we have 4 vectors. 1, 2, 3, 4. And each of them have 3 entries. So we can say by theorem, this is therefore, I don't know if I've addressed that. By Theorem 8, the set, sorry, I'm being sloppy. The set is linearly dependent. Okay, well, we cannot use Theorem 8 here because the number of vectors is equal to the number of entries. Okay, so we can't use or can't apply Theorem 8. But one thing we can notice is that we have a 0 vector. So since there is a 0 vector, the set is linearly dependent. And this is by theorem 9. Okay, let's look at the last example here. In this example, there are 2 vectors with 4 entries, so we can't apply theorem 8. There's not a 0 vector, so we can't apply theorem 9. So we need to address something else. And you'll see this a few times in your homework. What we want to do is see if one is a multiple of another. Okay, so let's see. If I multiply this column by -3/2, let's see what happens. Well, if I multiply -2 times -3/2, I get 6/2, which is 3. In this one, I get -12 divided by 2, which is -6. This one is -18 divided by 2, which is -9. This one is -30 divided by 2, which is -15. Oh no, -15, but that's a positive 15. So this is a problem. So the second vector is a multiple of the first vector, except in the last entry. So they're not multiples of one another. We can apply the other 2 theorems, so we can conclude that this set is linearly independent. So of these 3 sets here, only C is linearly independent. This concludes section 1.7.